Okay, hello everyone. Today we are continuing on the topic of deep learning applications to natural language processing. We've previously covered some basic material such as uh, converting words to vectors uh, and and n-grams and these kinds of ideas. Today we'll take it to a conclusion. We will begin with neural machine translation models. We've talked briefly about machine translation earlier on. We'll talk a little bit more about in depth about machine translation, that is converting language from text from one language into another language. And after that, we'll start discussing a topic that is receiving a lot of attention in deep learning. We'll discuss what are called attention models. And after we finish with attention models, we'll talk about a even more exciting variant called transformer models, all right? Transformer-based attention models. So those are the topics for today. That's quite a bit of material to cover. So let's begin with the neural translation. Okay, so the topic is neural machine translation. The reason it's called neural machine translation is machine translation based on neural networks. All right, so this is still a topic in natural language processing. We are into topic number 5, which is a significant size topic. And within neural machine translation, we'll start with an overview of machine translation, or MT. And first, we'll talk about a simple multi-layer perceptron approach to machine translation, then an RNN approach to machine translation that will lead us to using an attention mechanism and aligning pieces of data. We'll talk more. The next segment will be just on attention models. All right, example of translation. I just put down some examples of the translation task in the source language in English. If you say, would you like coffee or tea? And if the target language is, say, French, you would say, voulez-vous du café ou du thé, right? German is moktas du café oder tea. In Kannada, you would say, ನೀವು ಕಾಫಿ ಅಥವಾ ಚಹಾ ಬಯಸುವಿರಾ? And in Hindi, you would say, आप काफी या चाय पीना पसंद करेंगे? And in Tamil, நீங்கள் காப்பியாலத்து தேநீர் விரும்புகிறீர்களா? Or in Japanese, kohi kacho ja desuka? And in Chinese, niao cafe haishi cha. Right? Okay, I hope I pronounced your language properly in terms of machine translation going from English to any of these other languages. So formally, what is machine translation? Read a sentence in a natural language and emit equivalent sentence in another language. And it's a computer program to convert source text to target text. This shows French sentences converted into English sentences. So machine translation is a fairly important topic. Neural machine translation it becomes so good is eliminating demarcation between human and machine translation. And what are some advantages of this is improved human productivity, making machines more accurate going forward, and machine translation engines, several of them available: Amazon Translate, Crosslang, DeepL, Google Translate, Microsoft Translator, Unbubble, and Watson Language Translator. So many machine translation engines are available. So one approach to machine translation is called the proposal and evaluation approach. The two components. Proposal component suggests translations, and many translations will not be grammatical. Many languages put adjectives after nouns, so when translated into English, yield phrases such as apple red, right? Proposal mechanism suggests translation variants, ideally including red apple, right? So proposal mechanism has that. So there'll be some suggestions and there will be translation correction and so on. Language model evaluates the translations, assigns higher score to red apple than to apple red. So there's a proposal component suggests a translation, and a language model gives a higher score to something that is grammatically correct and so on. So this is probably a standard approach now. So history of machine translation, early systems used variants of n-gram models with back-off, maximum entropy models, and report the probability of a natural language sentence. So the first neural networks upgraded the language models and extended to conditional models. Traditional language models simply report the probability of a natural language sentence. Okay, machine translation produce an output sentence given an input sentence, extend the model to be conditional. Given this, what is the most likely? So it's a conditional probability. Straightforward to extend a model that defines a marginal distribution over some variable to define a conditional distribution over that variable given a context C, where C might be a single variable or a list of variables. So taking into account the context, translation is performed. And again, these are all conditional models. Okay, a multi-layer perceptron machine translation model produces a conditional distribution given the context where C is the single variable or list of variables. A multi-layer perceptron scores a phrase T1 through TK in the target language given a phrase S1 through Sn in the source language by estimating P of T1 through TK given S1 through Sn. So this was a straightforward multi-layer perceptron machine translation model that was finding the most probable sequence given the input sequence. And it beat the state-of-the-art statistical machine translation benchmarks. So this was a neural network based, but it was multi-layer perceptron. Disadvantage of multi-layer perceptron required input to be processed be of fixed length. So there was some length limitation. A recurrent neural network model provides ability to accommodate variable length inputs and variable length outputs. And an RNN represents a conditional distribution over a sequence given some input. So this again shows this kind of diagrams we've been saying that we have the X consists of some input, and then we have here uh, it's being processed at time t minus 1, time t plus 1, etc. So each of these inputs are going in and they're going into the hidden layer outputs here, and the hidden layers goes to the output. And here again we have the correct sequence, that is the y's, which are fed to the loss function, which now looks at the output of the neural network, and the loss function computes it. And then we use the derivatives to go and fix the network variables like v's here, w's. Not that the w's and the v's are all the same from one time instant to the next time instant, which is a characteristic of RNN type of models. So this was a kind of model which was able to give, so this is basically an RNN model, right? So this is, you can map inputs to outputs. RNN maps a single fixed length vector X into a distribution over sequences of Y. And here is an example of how RNNs can be used to predict words. For example, when you type in the cat sat on the, it's giving you probabilities associated with different words. So it can make a guess as to what the next word is. Like floor is the highest probability, bed is the second one, couch is the third one, and so on. And so these RNN model, one model reads the input sequence and emits a data structure that summarizes the input. We call this summary context C. C may be a list of vectors or vector or a tensor. This model may be an RNN, all right? So, and the second model is an RNN. It reads a context C and generates a sentence in the target language. This is the encoder-decoder framework. So the source object, French sentence, or even an input image. Encoder gives you an intermediate semantic representation. Decoder gives you an output object. In a sense, we are converting what was being input, which is a sentence, into some kind of a representation, which is captures the meaning of it in irrespective of the language. It is some kind of an interlingua. So the encoder-decoder architecture map back and forth between a surface representation, sequence of words, and a semantic representation called an interlingua, and uses the output of encoder of data from one modality, maps French to hidden representation capturing the meaning, provides an input to a decoder for another modality, maps from hidden to English. So it's like we are reading something in one language and mapping it to a mental representation, and then emitting that mental representation in another language. This idea has been applied successfully not just to machine translation, but also to caption generation from images. So it could have been an image that's input here, and it's capturing what is in the scene that it is seeing in the camera, and then it's outputting a sentence saying what it is. So this kind of training would be needed, where you present images and you would present descriptions, and you would do the mapping, and you would learn the weights needed. So RNN encoder decoder to generate output sentence condition or source sentence model represents the entire source sentence as an encoder. And early models only able to represent individual words or phrases. So these are all words. Of course, these words are all converted from word to vec, right? So these are all vectors coming in here, and we are mapping these into a context C here. That is, this is C, which is a representation of what was written here. And this could be like a hidden values here, and that's being used to generate the decoder sequence here. And of course, once we get a vector here, we need to generate what the input is by mapping these back. The opposite of the word to vec would be the vec to word type of operation. All right, neural models learn a representation in which sentences with the same meaning have a similar representation, regardless of whether they were written in a source or target language. So this is a bit more challenging than simply word to vec. It's like phrase to vec, that kind of a thing. Using an attention mechanism and aligning piece of data. So using a fixed size representation to capture the semantic details of a very long sentence, sentence of 60 words, let's say, is very difficult. Although it can be achieved by an RNN trained well enough and long enough, a more efficient approach exists. It's called the attention model. So we're saying that, the simple, straightforward idea of feeding a sentence and a long sentence to be able to capture everything in one vector and then presenting it is not such an easy task. An attention model is something that captures as to what it should remember. So an attention model, it is to read the whole sentence or paragraph to get gist or context, then produce translated words one at a time, each time focusing on a different part of the input sentence. All right, so what happens here is there are different types of attention models. We'll talk about it in the next segment on attention models. We have what's called as self-attention, where we evaluate as to which parts of the word are more important in any given context. And so remember those kinds of things rather than everything. The attention mechanism is used to focus on specific parts of the input sequence at each time step. So what is attention? It's how we correlate words in one sentence. So in this example of self-attention means attention within a sentence. There are two types of attention. One is called self-attention. The other one is called as general attention. Self-attention is looking within the input itself. Within, it could be a sentence or it could be multiple sentences. Attention within that. Whereas general attention would be to look at the attention model with the relationship between the input to the output. Let's say in machine translation, you're relating the attention from one to the other. So let's look at self-attention here. So this is saying when you're looking at a sentence like this, there is some kind of correlations happening here. She is eating. When you see the word eating, there is a correlation with apple. Right? It's not quite as highly correlated as eating green. She's eating a green. She's eating an apple. And this green doesn't go with eating, it goes with apple. So there is some connection. So we say between eating and green, there is low attention. And when you're eating an apple, there is a high attention. So there is some kind of stronger relationship that's being referred to as the attention here. Attention in deep learning is a vector of importance weights, right? So what we do here is we end up associating some weights with each word. So this word eating associates a weight with is, she, a, green, and apple, and says eating is high attention value to apple. Green has a high attention value to apple. Green doesn't have such a high attention value to a, or to eating, or is, or to she. So we can think of some kind of a vector for each word is saying, associating with each word, what is its higher degree of attention? With eating, it's apple, but not so much green, like that. Low. This is a low value, this is a high value. So for every word, there is some kind of a attention vector associated with all the other. So attention in deep learning is a vector of importance weights. In order to predict or infer a word in a sentence, we estimate using the attention vector how strongly it is correlated with. So when we say it's strongly correlated with, say, high attention, this high attention simply means it's eating is highly correlated with apple and less so with the others. So attention models and sentiment analysis. An example review. Pork belly equal to, this is some review. This is standard problem that is used in recommendation systems and so on, is you're automatically reading and determining whether it's positive or negative sentiment. So somebody is doing a restaurant review. Pork belly equal to delicious. Scallops. I don't even like scallops, and these were amazing. Fun and tasty cocktails. Next time I'm in Phoenix, I will go back there, go back here, and which means this is highly recommend. Highly recommend is the summary. So the attention model learns that out of the 5 sentences, first and third are more relevant. Furthermore, the words delicious and amazing within those sentences are more meaningful to determine the sentiment of the review. So sentiment would be a positive review. And so this says for that positive review, these were the prominent ones. So these were the ones that relate to that sentiment. So attention models play a role not only in machine translation, but in other NLP, such as sentiment analysis. So this one shows a little bit more about this attention mechanism. C is a context vector. It's a weighted average of feature vectors H and weights alpha T. So we have these hidden unit values coming from the input, and it's a weighted average in the sense each of them is multiplied by an alpha. HT minus 1 is multiplied by alpha T minus 1. And similarly, HT is multiplied by alpha T, and HT plus 1 is multiplied by alpha T plus 1. Together, they form addition of all of these plus here forms the context. So the context C, although it's just one element, it has got all these internal representations of the words and their weights associated with them. And the feature vectors H are hidden units in a network, but they may also be a raw input to the model. They could be just words, word to vec, or it could be the hidden unit values. So this is capturing what was actually presented here. What was the sentence that we had? So the weights of the attention model, what are those things, alphas, are produced by the model itself. They're usually values in the interval 0 to 1 and are intended to concentrate around one edge so that the weighted average approximates a reading that one specific time precisely. So this is the weights are learned in the training process in terms of the task at hand, maybe a proxy task at hand. Attention model can be trained. The attention mechanism is more expensive computationally than directly indexing the desired edge. But direct indexing cannot be trained with gradient descent. And the attention mechanism based on weighted average is a smooth differentiable approximation that can be trained with existing approximation algorithms. So all of this is trained with the back propagation to learn even the weights over here. So the three components of attention are an attention-based system has three components. A process that reads raw data such as source word in a source sentence and converts them to distributed representations with one feature vector associated with each word position. I've got some more examples coming up that will kind of illustrate this better. A list of feature vectors storing the output of the reader. This can be thought of as a memory. Containing sequence of facts which can be retrieved. Okay. A process that exploits the content of the memory. Okay, so there is more to the three components of the attention mechanism. And relating word embeddings. When words in one language are aligned with corresponding words in a translated sentence, we can relate corresponding word embeddings. So in the early work, learn translation matrix relating word embeddings in a language with word embeddings in another, yielding lower alignment error. So this would be the same number of words and so on, extensions on cross-lingual word vectors. So there's been a lot of water that has flown under the bridge here. Machine translation is one of the oldest topics in computer science, saying people wanted to translate Russian to English and so on. So the attention model that we just talked about, where somehow, we'll talk about it more in the next lecture. But that seems like an important topic here. Was first introduced for machine translation 2014, about 5-6 years ago. Now widely used in neural networks for NLP, statistical learning, speech, computer vision, etc. And attention models are state of the art for tasks of machine translation, question answering, sentiment analysis, part of speech tagging, dialogue systems, and so on. And there are advantages beyond improving performance, improving interpretability of neural networks, which are otherwise black box models. So interpret in the sense, you can get a good explanation as to why was it obtained like this, and overcome challenges with RNNs. The basic RNN does not have the attention model. Here in an attention model, we are bringing in some of these weights, and those play a role in the context. Okay. So let's go on to a full set of slides here just on attention models. Okay, so I spoke about attention models are important. So let's learn a little bit more about them. So yeah, the previous set of slides were on neural machine translation. This one is just on attention models. So the topics here is what is an attention vector? That's the C vector we just saw earlier on, attention vector. And we'll talk about general attention and self-attention. And encoder-decoder model is a simple model without attention. And the types of attention models, and encoder-decoder with attention, and neural network for self-attention. All right, so it's all about attention. So, all right, what is attention? All right, can I have your attention, please? right? Okay. In Italian, it says attenzione. In German, Achtung is attention. In French, l'attention. In Kannada, it's gamana. In Hindi, it is dhyan. In Tamil, it is kavanam. It means to focus on something and take notice. All right. The word attention comes from that. Paying greater attention to certain factors when processing the input. That's the idea of attention. So, general and self attention. The attention component of a network manages and quantifies the interdependence. Right? So what is the dependence between the words? We saw some examples. She was eating a green apple. So it quantifies the interdependence between words. General attention is between input and output elements. So if we are doing machine translation, the input was, how was your day? And in French, it is comment s'est passée ta journée, right? And this is saying the relative importance for each of these outputs. The first word was most important, second less, and the last two were least for this generation of this word here. Let's say it's the training model. We're saying, how was your day? Comment s'est passée ta journée? So it is learning that the first word is the most important for this, second word less. For this one, first and second was the most important. For this one, again, the second was the important one. Here, the third was the important one. And this one, it says the fourth one, like day. The day would be the journée here. So this is the kind of attention that would be generated as to relatively saying how important are for each of these words. So that information is what is being, this is part of the attention vector. So this is between input and output, that's general attention. Self-attention was the kind of thing we saw earlier on, which is she's eating a green apple. So this is not between input and output, which is just within input elements. It's saying, okay, how do these things relate to each other? What is the relative importance of these? Attention vectors in neural machine translation. For a neural machine translation, for each output word, assign higher weights to relevant words in input. Higher weights, so we just saw this example. English to French translation. How was your day? And it's comment s'est passée ta journée. And for each output word, how much important was each of these words? So that is what is called as the attention vector. Again, the self-attention case we saw. Attention within, self-attention is attention within different parts of the same input. So here is a longer example of self-attention vector. Supposing, we want machine learning system to learn relationship between words in an input sentence. Supposing it said, the animal didn't cross the street because it was too tired. So there is a lot of interrelationships going on right there. This is not a machine translation example. This is just as input sentence. And this says there is some relationship. What is the? The relates to the animal. And then the animal equates the animal that was crossing, and the animal was crossing the street, and the animal was tired. Okay, all these things. So it's the same set of words here repeated here, except it is saying the gives a high priority to animal here, and it gives a high priority to street here, and lower to cross and so on, and the here. So there is some kind of strength to these. So this is self-attention vector. So this vector itself, as what is the attention that each of the words gives to the others. And that is regarded as an attention vector. For each word, there would be a different attention vector. Color coding shows that there is some connection between animal, cross, street, and the, because they're all related to animal, the subject of the sentence. So these are all related concepts here, and this is what has to be learned here. So how does one compute the importance of uh, words to each other, it is not that complicated, interestingly, the self-attention process. So self-attention is a process. A sequence of vectors x, here is a sequence of vectors, x1, x2, x3, x4, x5. The cat sat on the is encoded into another sequence of vectors z, which is over here, z1, z2, z3, z4, z5. Its corresponding z vector represents both the original word. The word was just original word. Okay, so if yeah, x1 is a word, and it relationships with the other words around it. So the z vector corresponds to the original vector. So z has the word x1 in it, as well as some relationship to the neighbors. So how do we compute the z's from the x's using this attention model here? It's a process. Self-attention is a process that generates these here. And that idea is illustrated in this simple way using what's called as cosine similarity. Cosine similarity is a very commonly used concept in pattern recognition, where we say if I give you two vectors and ask you how similar the two vectors are, you would say, well, take the cosine similarity between them. And the cosine similarity is obtained by taking the cosine of the angle between them. Supposing I have two vectors, x1 and x2 in vector space, the angle between the two, if the angle is 0, it means they are exactly along the same vector. So it's cosine of that angle, cos 0 is 1, right? So it will be high. If the angle is large, then the cosine will be small, which means they're not that similar. So that is the idea of cosine similarity. Cosine similarity, interestingly, is related to the dot product between the two vectors. So the x1 times x2, the dot product of these two vectors, is equal to cosine of the angle A between x1 and x2, and this is the magnitude of the two vectors, x1 and x2. So the dot product is proportional to the cosine of the angle. So if the cosine of the angle, if it's a value between 0 and 1, so it gets a high value when the angle is 0. Right? So if this is the case, let's just do dot products. So we have the input, the cat sat. We're only looking at these three words here, let's say. And we want to look at what is the similarity between cat. Of course, these are vectors, right? These are all word to vec. These are all vectors that have been obtained. And this says compute the cosine between the neighboring words. So we are saying this quantity is x1. See, we are trying to do this for x2. So we're multiplying x2 with x1. This is x2 transpose x1 here. And then we are getting x2, we do that for the word itself, x2 transpose x2. And then we're doing here x3, x2 transpose x3. So we have got, we say this is a weight, this is a weight, this is a weight. And these are what are called as raw weights, W2J. So this we refer to as W2. X2 has a weight W2. And then W2 is nothing but X2 transpose X1 here, all right? X2 transpose X1 is this one. X2 transpose X2 is this one, is X2 transpose X3 is this one. So we refer to them as raw weights. So what is happening is we are getting a sense for how closely aligned X2 is this one and that one. And we have got some raw weights here. And then what we do is we do a softmax of these weights. Given this is W21, W22, W23, right? W2 means it corresponds to X2. And this is 21, this is 22, this is 23. And we softmax the 3, which means we are going to be coming up with values that add to 1 with the weights that you've just computed in this way. And we use that to compute Z2. So this X2 is going to generate Z2. And how does it generate Z2? It is given by W21X1, W22X2, W23X3, linear combination of this, add them together, you're getting Z2 over here. So that corresponds to its local contextual information. That's the attention information. So we are saying corresponding Z vector corresponds to both the original word and its relationship to the other words around it. So we have both together represented in Z2. It knows what the original word is and what is the contextual information around it. So this is referred to as the self-attention process. So there can also be multiple attention vectors. So we saw the example, the animal didn't cross the street because it was too tired. And this is provided, cross, for example, has got weights for all these words like high with because and tired and so on. And there could be a slightly different context, and this could be another vector over here. And the same input can have multiple attention vectors. We might be looking for, in some other situation, what could it be? And that could be also another vector like that. So they've got all these variants. So we discussed 5 attention models: basic encoder-decoder recurrent neural network model without attention. Right? We saw some of it earlier on. We'll again look at it, encoder-decoder model. And we're talking about machine translation type of problem here. And after that, we look at encoder-decoder RNN with attention. And then we look at a variant called a transformer model with no recurrence. And generative pre-training of attention model. And this is a Google system that is revolutionized things called BERT, is a bidirectional encoder, right? With transformer, right? With no decoder using bidirectionality. So in the idea of encoder-decoder without attention, we saw the idea of a context vector C. So if you have encoder saying, would you like coffee or tea in English? The decoder has to convert it into voulez-vous du café ou du thé in French. But it goes from English to French via a sentence embedding. So this sentence is being embedded into a context vector of length 5. So this is the context vector that is being generated. And from this we generate the decoder output. Let's see, here's another example. Would you like coffee or tea? From English, we're going into a decoder, which is Kannada, which is saying, Nivu coffee atwa chaha bayasuvira, right, in Kannada. So we have a conversion from English to other languages based on a recurrent neural network. There is no attention being used as such. It is just a mapping using the kind of architectures we saw, and we'll again see it soon enough. And so the encoder compresses the input sequence into a context vector. It's a sentence embedding or thought vector of a fixed length. It is expected to be a good summary of the meaning of the whole sequence. This is the interlingua idea. The meaning of this sentence is being expressed by these set of numbers. Decoder is initialized with the context vector to emit the transformed output. So decoder does the magic of converting this back into the other language. So the basic RNN-based encoder-decoder is, this is one more diagram of the same thing. We have an encoder x1, x2 through xn. And these are the word embeddings here. This is the word to vec. This is an English word, x1, x2, so on. It's becoming some numbers here we refer to as word embeddings. These word embeddings are being mapped into a hidden representation. These vectors become H1E, H2E, HNE. And then this HNE is being output to the decoder RNN with values H1D, H2D, HMD. This is a different, could be different length, and it is being generated. This is E for encoder, D for decoder. And these values now are going to produce the outputs that correspond to the text in the languages. And there is some kind of a softmax relationship going on here between in generating these outputs, and that would be the decoder RNN. Arbitrary input and output lengths here. At position T, HTFE and HTFD are the hidden states of the encoder and decoder RNN respectively. And final encoder hidden state HN of E, which is this one here, serves as the context for H1 of D in decoding. And both the encoder and decoder are RNNs, and it could even be an LSTM or a GRU, one of those standard RNN methods. So this is an RNN-based encoder-decoder. There is no attention model. It is the last of these hidden states that, look at this hidden state here. It's capturing information not only from XN, the last word, but it has got all these inputs coming in. So this is kind of representing what all has been seen so far. And that sequence is what is giving rise to the output. Sequence to sequence RNN models. Okay, encoder and decoder have the same structure RNN. Encoder encodes the input sequence into fixed length vectors H1E through HNE. And the decoder takes a single fixed length vector HNE as input and generates Y1 through YM. And it uses what's called auto regression, consumes the previous output. Right. So summary of encoder decoder is it takes an input sequence, encoder, context vector, decoder produces the output. So simple RNNs, LSTMs, GRUs, CNNs, transformer networks. Encoder could be any of these. Only a single network layer is shown. In a stacked architecture, output states from a top layer are taken as a final representation. A widely used encoder design makes use of stacked by LSTMs. So that's for the encoder. Decoder, auto-regressive generation is used to produce the output sequence, an element at a time, and so on. So the deficiency, so this is the preamble to where we are heading into attention-based model. The previous one we saw does not have attention. Encoder compresses all input into a single fixed length vector HN to be passed to decoder, leads to loss of information. Unable to model alignment between input and output sequences, which is essential for structured output tasks such as translation or summarization. Intuition of what is needed. So this idea of using RNNs to do machine translation was being used, and it did pretty well, but it was still falling short. In sequence to sequence tasks, each output token is expected to be more influenced by some specific parts of the input sequence. However, decoder lacks any mechanism to selectively focus on relevant input topics while generating each output token. So this is saying we expect each output to be influenced by some specific parts of the input sequence, right? Not just that word, but others, and more specifically some, but not all. And decoder lacks any mechanism to selectively focus on relevant input text. So there should be a selective focus on which ones should be influencing it. So this leads us to encoder-decoder RNN with attention. All right, so that is this first diagram we already saw. That is basic encoder-decoder without attention. Now we look at encoder-decoder with attention. And after that, we look at transformer model with no recurrence, generative pre-training of attention models, and then BERT with no decoder using bidirectionality. I've shown some diagrams here illustrating what the architectures look like. So this is these two diagrams show encoder decoder without and with attention. We just saw this diagram. Basic encoder decoder, final encoder hidden state serves as context for HND in decoding. So that was the basic encoder decoder. The attention model version, there's a slightly different architecture. It's got the same sequence here, but this is now creating a context vector C. And this context vector C also takes back what has been generated in the first output here. And this context vector C has elements Ci, alpha ij, hj of I. So these are hj of I. These alpha j's are softmax of these hi's here. And these alpha ij's, these weights together form a context vector over here. So accesses the entire encoded input, induces attention weights over input. So there is some alpha ij that come into play. Dynamically updates during decoding and can be embodied in a fixed size vector. All right. So there is a specific mechanism that's going on here, which is all of these hidden vectors together. What is the difference between this and that is the earlier one, there was only one vector that was produced by the RNNs together. This one is retaining all of this information, H1 through Hn, and weighting each of these and using that information in this vector C sub I, and that is in turn being output to these to this yi. Ci is going to this yi. So that context is coming into play. Ci for the, you note the subscript here, hi, this is Ci, and Ci is going over here. So we'll be doing that for every one of these. So the context is playing a role with each of these. So there's something more happening here with the attention mechanism, which is taking into account the neighborhood information. So encoder decoder with attention, we just saw that example. This gives all the equations properly. Decoder hidden state HID is based on the previous state HI minus 1D, previous word generated YI minus 1, and current context CI. So HI of D is G of YI, HI minus 1, and CI. So all of these come into play. And the context vector CI, which is this one up here, obtained by comparing the previous hidden state to all of the encoded hidden state. And score is a measure of similarity of the decoder hidden state to each encoder hidden state. And the alignment score functions are dot product. We just saw the dot product has something to do with similarity. It's saying these dot products, and it shows the detail of the score. There are different options here. Dot product is the simplest one. Another one is called general weight matrix. And a neural network determines the attention weights alpha ij. And it is based on, looks like the softmax here we are doing of these scores. And they're all, when we do a softmax, remember it goes to a value between 0 and 1. And these alpha ijs come into play. The context vector for output yi is coming from Ci. And these are the weights alpha ij, which are values between 0 and 1. And those are what are multiplying the HA together. And so this is referred to as encoder decoder with attention. And then there's a variant called bidirectional encoder. Encoder is a bidirectional RNN. So this is H's here are going forward and this is H's are going backward. And there are all these alphas going along with it. And there is similar softmax happening here. CIs look quite similar. And all of this together is now used as the context or the attention for each word. So in a way, for each word, there is something happening in terms of vectors coming in from the other parts of the input. Example of alignment matrix alpha ij. Matrix of alignment scores is a byproduct to explicitly show the correlation between source and target words. Alignment matrix of French input and its English translation. So this says here are the words in English here, and these are the words in French. And it is capturing what is the alignment between these words. That information is being alpha ij is referred to as the alignment matrix, and the values between 0 and 1. That's what's being illustrated here. Alignment score functions. There is content-based attention, additive, location-based, general. Here is dot products, which we just saw. Dot product is a measure of similarity, but there are so many variants here. And there are all these papers that have come out, which I guess the most recent of this is simply to use a scale dot product. That seems to be the most recent one. So we just saw the idea of self-attention, also known as intra-attention, relates different positions of a single sequence to compute a representation of the same sequence. All right, so there is broad categories of attention or self-attention relating different positions of the same sequence. Theoretically, self-attention can adopt any score function above, but just replace the target sequence with the same input sequence. Global is attending to the entire input state space. And local, attending to the part of the input space, patch the input image, and so on. This one is a very specific slide about a neural network for learning the alpha ij, and it shows how the setup is. Here's the H1s here, and there's a neural network to compute this alpha matrix over here, which gets utilized to get the context vector, which is the alphas times the h's, right? How that is learned. So this is Tensorflow, which is available at tensorflow.org. Neural machine translation with attention. And it's again showing I am a student is the input and je suis étudiant is the output, which is the translation, right? This is so you're giving I am a student and je suis. This is the translation from English to French. And this is capturing the attention weights, which add up to 1, as you can see, and you get a context vector. And that gives you an attention vector, which captures the inputs and the initial words that have been presented in the training part, which is now producing the output. I guess the training part, this is producing a correct output, same as the input here. And an example like this with plot of attention weights and so on. Okay, so hopefully you got a sense for the idea of RNN without attention and then RNN with attention. And that's what we saw just now. Okay, so the last part is called the transformer models. Okay, we are still talking about attention models. It's a more recent variant of it called transformer models. And what are we going to read at transformer models? Types of attention models, the transformer model, and then full transformer with attention, and then multi-head attention, and improvements to the transformer. Okay, a famous one is called generative pre-training, GPT. And then Another improvement is a transformer called bidirectional encoder representations from transformers called BERT. So we were just looking at encoder decoders. We're talking about a bidirectional encoder, both directions in the encoder from transformers. So a transformer is a variant of the attention models. Right? So this is transformer model with no recurrence first. Transformer is an attention mechanism again. It leads to contextual relationships between words. It includes two mechanisms, an encoder that reads the input text, a decoder that produces a prediction for the task. Model has no recurrence. So we previously saw that the models had some kind of a relationship from one stage to the next stage. Self-attention to represent input-output without RNNs. So it uses self-attention to represent input-output without, okay, with self-attention, we saw that it is some kind of a vector that shows what is the relationship between neighboring words. It allows more parallelism, high translation quality, state of the art, training 12 hours on 8P100 GPUs. Okay. So the transformer model has an encoder-decoder architecture. Encoder maps input x1 through xn to representation z equal to z1 through zn. So given z, decoder generates y1 through yn element y's. So it's got an encoder-decoder architecture. At each step, model is autoregressive, consumes previously generated symbols as additional input when generating the next. So a stack of encoders here, encoder, 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 Jésus étudiant is going through the encoders. And then it's being translated into English. I'm a student. It's going through these decoders, stack of decoders. And the stack of decoders are used here, this transformer model. So the encoder and decoder use attention. So you have an encoder on this side and a decoder on this side, and there's an auto regression, consume previously generated output. So the encoder and decoder are stacked. And see next slide, we'll look at that. Self-attention is going on, point-wise, fully connected layer. So there is an input embedding, an output embedding. So we're using machine translation. We are training it, saying here's the input embedding in this language and input embedding in the other language. And this is an encoder architecture, multi-head attention. We talked about how the attention models can have multiple vectors. So that's the idea of multi-head attention. And we have here the output embedding, which is obtained from the encoder here. And again, a feed-forward network, linear softmax output probabilities in terms of different possibilities that it might generate. Stacked encoder decoder, we saw this design earlier on. And self-attention again is being illustrated. It uses the idea of self-attention, input sentence to translate. Second law of robotics. A robot must obey the orders given it by human beings, except where such orders would conflict with the first law. If you had a paragraph like that, so we need to have these attention, self-attention we saw. When it say it refers to the robot, such orders refers to the earlier part of the law, second law or previous law. The first law refers to the entire first law. So there is something, the first law. So there is all these relationships exist between words or phrases. Highlighted words refer to other words. It refers to the robot, such or etc. This is what self-attention does. It bakes in the model's understanding of relevant and associated words that explain the context of certain words before processing that word, right? So it bakes in the model's understanding of the relevant and associated words. So what are the associated words? And explain the context of a certain word before it makes the translation. By assigning scores to how relevant each word in the segment is and adding up their vector representation. This slide is something that illustrates the idea of self-attention that's being used in these transformer models. The self-attention layer is paying attention to a robot when it's processing the word it. The vector it will pass to its neural network is a sum of the vectors for each of the three words multiplied by their scores. Self-attention is processed along the path of each token in the segment, so on. Okay, so this kind of tries to illustrate and explain how the neighboring words are in the self-attention process. We saw that earlier on. It is using the neighboring words to figure out what is its importance by looking at the dot product and so on. So full transformer with attention involves these interesting looking diagrams here. We saw this one, full transform with attention. What this multi-head is expanded into this diagram here. And then what is the scale dot product has got this kind of a design over here. All of this is said to be the full transformer with attention, which does not use RNN, but uses a straightforward vector representation. Transformer encoder detail. So it says what each of these diagrams are. It's trying to explain that. It's getting a bit complicated here. Transformer decoder detail. Okay. So the three things important in these transformers are query, key, and value and attention, in the attention mechanism part of the transformer. All right. To compute next word in translation, attention mechanism creates a vector using the source sentence and what has been generated so far. That's the basic idea. So we have using the source sentence and what has been generated so far, all of this being put together. And these are all captured in these three things called Q, K, and V, corresponding to the three elements, query, key, and value in the attention mechanism. Query, key, and value. Some more example of query, key, and value. And detail of scaled dot product. This is dot product attention. We saw that idea of dot product of the attention. And this is more detail about the multi-head attention. All right, so transformer model with no recurrence. There is no recurrence relationship with a transformer model. And generative pre-training of attention model, improvements of transformer. So OpenAI, these are the state-of-the-art things that are going on today. OpenAI, Paul Allen's company, which came up with this GPT, generative pre-training, combines supervised and unsupervised learning to improve word vectors. It uses combines unsupervised and supervised. Performs generative pre-training. State of the art for the following tasks: textual entailment, semantic similarity, reading comprehension, common sense reasoning, linguistic acceptability, multitask benchmark. So this kind of revolutionized things. Google's BERT is a bidirectional encoder representation from transformers is an improvement of GPT. Right. Key technical innovation is bidirectional training of transformer. Well, GPT used to have GPT-2. Now I think they've come up with GPT-3. Maybe that has overcome BERT. So GPT-2 generates human-like output. For example, we saw this example earlier on, trained to predict next word of 40 gigabyte internet text. If cat sat on it has digested lots and lots of text saying, most probably it's going to be floor. While trained to predict the next word, it surprisingly learned basic competence in tasks like machine translation and question answering. That's without ever being told that it would be evaluated on these tasks. It just digested lots of text. It developed a higher competence in machine translation. And here is an example of the remarkable text generation that GPT-2 can do. GPT-2 generated synthetic text. System prompt, human written. Let's read this because it's fun. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley of the Andes Mountains. Even more surprising to the researchers was the fact that the unicorn spoke perfect English. So this is a nonsensical human written prompt. They typed it into GPT-2 and see what it would generate based on this. What would be the next prediction? It was not like the cat sat on the mat. That was just a word. Here it is generating sentences of text. So the next sentence was, the scientists named the population after the distinctive horn. This is the model completion. It's naming that Ovid's unicorn. It's named that. The four-horned silver-white unicorns were previously unknown to science. So it's making up that it's a four-horned one. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, so it's a name from this a Spanish-sounding name, an evolutionary biologist from the University of La Paz, which is, I guess, close to the Andes Mountains. So it knows about that. Several companions were exploring the Andes Mountains, then found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain surrounded by 2 peaks of rock and silver snow. It's making up all of this. Perez and others then ventured further into the valley. By the time we reached the top of the peak, the water looked blue with some crystals on top, said Perez. Perez and his friends were astonished to see the unicorn herd. These creatures could be seen from the air without having to move too much to see them. They were so close together that it touched their horns. All right. So this is the remarkable expertise of something like GPT-2, which is generating natural language text after digesting a large quantity of text. And so this is what is prompting all this discussion of fake news and things like that. So one can type in something nonsensical here and you can generate a whole story behind it with no basis in reality. So the architecture of GPT and text and position will be transformed to vector. Text and position transformed to vectors, passed to multi-head self-attention, combining results from step 1 and 2 and performing a normalization, passed to a fully connected feed-forward network, combining results from step 3 and 4, performing a naturalization. Finally, combining multi-head together, computing vectors, text prediction, text classifier, and so on. GPT, it's an OpenAI multi-layer, the OpenAI is the name of the company, multi-layer decoder. Unsupervised pre-training task is language modeling. Supervised fine-tuning, multitask learning. So it's some combination of these. And input formatting for GPT is classification, entailment, similarity. There are some nitty-gritty details of how they went about training it. And the last of these sections is BERT, which is the Google system, bidirectional encoder representations from transformers. Uses transformer attention mechanism to learn contextual relationship between words. Transformer includes two mechanisms, an encoder that reads text input, a decoder that produces prediction for the task. Since BERT's goal is to generate a language model, only the encoder mechanism is necessary. So this is a generator, right? So it generates text and there's no machine translation as such. Uses bidirectional training, deeper sense of context flow than single direction. So this is bidirectional, whereas the GPT was not bidirectional. That's why this BERT uses the B here, bidirectional. MAST LM uses bidirectional training. The structure of BERT is seen in this diagram. And the BERT encoder block implements the base version of BERT network. It's composed of 12 successive transformer layers, each having 12 attention heads. Total number of parameters is 110 million in this network. I saw there's been a huge controversy in the last month or so. I think there's even some workshop today being held on this paper from Google, and the person who wrote that paper was fired from Google. And she was talking about how this work on these generating text and all that, some ethical issues and so on. And in that paper, they talk about what does it take to train a network. I think they give even larger number than this. Training of GPT-3, I think, GPT-2 or GPT-3 is about 230 million parameters. And they compared how much energy is needed to run computers to generate, to determine 230 million parameters for the network. And I was astounded to see some of the numbers. It says, they compare the amount of carbon dioxide emitted to the atmosphere by running that much of computing, and that's way, way, way larger uh, than many things, such as if you're flying from San Francisco to New York, it's a very small amount of carbon dioxide per person on a plane. And then they compare it to a few other things, such as a car in its lifetime. A car in its lifetime, maybe 10 years a car lives, how much carbon dioxide does it generate to the atmosphere? They say that's much smaller compared to training a GPT-3 or something with 230 million parameters. Comparison of BERT and GPT. BERT is an improvement on GPT. That's GPT-2 it was. The main differences are bidirectional training, different pre-training tasks, mass language, trained on a much bigger corpus, book corpus of 800 million words plus Wikipedia, 2,500 million words. 3 times as many parameters as the large version, pre-trained model for 102 languages. And there is something about the bidirectionality here, which is fairly straightforward. Text pre-processing, BERT, it's pre-processing position embeddings, segment embeddings, so on. Okay, BERT is pre-trained on 2 NLP tasks, masked language modeling for bidirectionality, next sentence prediction. What are these things? Masked language model is what's described here. Word prediction using masking, next sentence prediction, and then BERT architecture. All right, summary and conclusion. Attention has revolutionized NLP models, now a standard fixture for NLP, because it enables a model to remember all words in the input and focus on specific words when formulating a response. Early models were sequence-to-sequence models with RNNs. Okay, we're talking about this whole discussion on NLP. And the recent models are self-attention and transformer models. Google's BERT, OpenAI's GPT, and XLNet are more popular today based on self-attention and the transformer. All right, so my own presentation comes from a lot of these sources here. All right, transformer attention models. The paper was this one by Vaswani. All you need is attention. That's the paper on that. The encoder-decoder, the basic ideas comes from Jurafsky and Martin's 2020 book, Speech and Language Processing. GPT has got some nice stuff here. BERT has some nice stuff here. So anyway, it's pretty exciting to read about all these things. And it's making the news in a big way about the future and the ethics of AI, because it has become so powerful, right? Okay, I will stop here on my discussion of the natural language processing application. And we have come to the end of the semester here. So I will take your questions now offline.